Imagine you are watching a friend fall into a black hole, not close enough to be in danger yourself. You are at a safe distance, watching through an impossibly powerful telescope, and your friend is drifting, feet first, toward the event horizon, the point of no return. Here is what you would see. At first, your friend falls normally, accelerating as you would expect towards something with enormous gravity. But as they get closer to the event horizon, something strange begins to happen. They start to slow down. Not because they are slowing down, they are still accelerating from their own perspective, but because the gravity near the event horizon is so extreme that it is warping the very fabric of space-time itself. Time, near a black hole, does not pass at the same rate it does where you are watching from. Your friend slows, and slows, and slows. Their image reddens. The light they are emitting is being stretched by gravity, shifting toward the red end of the spectrum. They become dimmer. The light they are sending toward you is losing energy as it climbs out of the gravitational field. And then, from your perspective, they stop. They do not cross the event horizon. They hover at the edge, frozen in time, growing redder and dimmer and more ghostly until the light they are sending becomes so faint and so stretched that it effectively disappears. From where you are standing, your friend never falls in. They are frozen at the edge of the black hole for eternity. Now. Here is the thing. From your friend's perspective, none of that happened. They felt no sudden slowdown. They noticed nothing unusual at the moment of crossing the event horizon. They fell straight through, and they are now inside the black hole. Both of these things are true at the same time. Both perspectives are equally valid descriptions of reality. And this is where the real story begins. Before we go any further inside, we need to be clear about what a black hole actually is, because the popular image, a dark sphere sitting in space, sucking everything in like a drain, is misleading in some important ways. A black hole is a region of space where gravity is so extreme that nothing, not matter, not light, not information of any kind, can escape from inside a certain boundary. That boundary is the event horizon. It is not a physical surface. There is nothing there to touch or see or bounce off. It is a mathematical boundary, a point of no return defined entirely by the relationship between gravity and the speed of light. Inside the event horizon, the escape velocity, the speed you would need to travel to get back out, exceeds the speed of light. Since nothing in the universe can travel faster than light, nothing that crosses the event horizon can ever get back out. Not because of a wall or a barrier, but because of the geometry of space-time itself. At the center of the black hole, at least in our current equations, is a singularity, a point where matter has been crushed to infinite density, where the known laws of physics cease to produce meaningful answers, where our best mathematical descriptions of reality simply break down. The singularity is not a thing, it is a gap in our understanding. It is where general relativity, Einstein's description of gravity and spacetime, stops working. Physicists generally believe that a complete theory of quantum gravity would replace the singularity with something physically real, but we do not yet have that theory. Black holes come in dramatically different sizes. Stellar black holes, formed when massive stars collapse at the end of their lives, typically have masses between a few times and up to around 100 times the mass of our Sun, with LIGO and Virgo detections having revealed some reaching toward that upper bound before crossing into what astronomers classify as the intermediate mass category. Supermassive black holes, found at the centers of most large galaxies, including our own Milky Way, have masses millions or billions of times the mass of the Sun. The one at the center of our galaxy, called Sagittarius a star, has a mass about 4 million times that of the Sun. And they are not, it should be said, cosmic vacuum cleaners waiting to suck you in from a distance. A black hole, with the same mass as the Sun, would have the same gravitational pull as the Sun from any distance outside the event horizon. You would not be pulled in unless you were already close enough that you would have been pulled in by the Sun too. It is only if you actually get close that things become extraordinary. Let's say you are falling toward a black hole. What do you experience on the way in? At great distances, nothing unusual. You feel the pull of gravity, accelerating you toward an invisible point in space. You would see the stars around you beginning to distort, a visual effect called gravitational lensing, where the black hole's gravity bends the light from distant stars around it. The sky would look increasingly strange, with stars seeming to cluster and shift and bend as you moved closer. As you got closer, the black hole itself, despite being invisible, since it emits no light, would be visible as a perfect circular shadow against the background of stars and any surrounding material. This shadow, called the black hole's shadow, is actually slightly larger than the event horizon itself. The strong gravity bends light paths in a way that makes the dark region appear about 2.5 times larger than the event horizon's actual radius. In 2019, astronomers captured the first actual image of a black hole's shadow, the supermassive black hole at the center of galaxy M87, 55 million light-years away, and it matched the predictions of general relativity almost exactly. As you fell further in, the gravitational pull on different parts of your body would begin to differ. Your feet, if falling in feet first, would be pulled more strongly than your head, simply because they are closer to the singularity. This difference in gravitational force across your body is called tidal force. For a small black hole, a stellar black hole with a few times the mass of the Sun, this tidal force would become lethal long before you reach the event horizon. The difference in pull between your head and your feet would be strong enough to stretch you out lengthwise while simultaneously squeezing you inward from the sides, a process physicists call, with genuine affection for the absurdity of the name, spaghettification. You would be stretched into a long, thin strand of matter, like cosmic pasta, as the tidal forces overwhelmed every other force, keeping you together. For a supermassive black hole, however, the kind found at the centers of galaxies, the event horizon is so vast and the tidal forces across the relatively tiny span of a human body are so mild at that scale that you would cross the event horizon without feeling anything unusual at all. No dramatic sensation, no physical threshold crossed, just a mathematical boundary passed, indistinguishable from crossing any other point in empty space. The size of the black hole determines entirely whether the crossing is mundane or catastrophically violent. So let us say you are falling into a supermassive black hole and you cross the event horizon. What happens? Nothing. At the moment of crossing, nothing detectable happens. You feel no jolt. No alarm goes off. There is no sign, from your perspective, that you have passed any threshold. The stars behind you still look roughly normal, though increasingly distorted. You are still in freefall, weightless, the same as you were before. But something has changed irrevocably. You have crossed the event horizon, and physics at this point has some very strange things to say about what that means. Inside the event horizon, the concept of direction changes in a way that is genuinely difficult to articulate. Outside a black hole, space extends in all directions and time flows forward. Inside the event horizon, the direction toward the singularity becomes, in the mathematics of general relativity, more like a direction in time than a direction in space. Moving toward the singularity is not like moving toward a wall you might be able to stop before you hit. It is like moving toward tomorrow. You cannot stop Tuesday from coming. You cannot reverse its direction. The singularity is not a place you are moving toward. It is a moment in your future that is inevitable from the instant you cross the event horizon. There is no escape, not because of an irresistible physical force pulling you inward, but because the geometry of space-time inside the horizon makes all future-pointing directions lead toward the singularity. You cannot travel away from it any more than you can travel into yesterday. How long would you have? The maths here is precise enough to be humbling. For a typical stellar black hole of around 10 solar masses, the journey from the event horizon to the singularity takes roughly 1/10 of a millisecond. You would not have time to think a single thought. For Sagittarius A star, the 4 million solar mass black hole at the center of our own galaxy, the fall would take about a minute. For a standard supermassive black hole of 1 billion solar masses, you might have several hours. And for the most extreme objects in the known universe, ultramassive black holes like TON 618, weighing in at around 66 billion solar masses, you could have up to 11 or 12 days of free time inside the event horizon before the singularity became a problem. Days in which, in principle, you could look around at the interior of a region of the universe that no signal, no light, no information can ever leave. What you would see there, if you could see, We genuinely do not know. Our equations break down too close to the singularity to say anything reliable about what the final moments look like. Let's go back to the person watching from outside, because the frozen image they see of you hovering forever at the edge of the event horizon raises a question that should genuinely disturb you. If the outside observer sees you frozen at the horizon for eternity and you experience falling straight through, which one is reality? Which one actually happened? Both. This is the part where our everyday intuitions about how the universe works fail us completely, because they are built on an assumption that turns out to be wrong. The assumption that time is the same everywhere. It is not. Time passes at different rates in different gravitational fields. This is not science fiction. It is a measured, documented, experimentally confirmed fact. The GPS satellites orbiting Earth have to account for this in their software. Their clocks, sitting in weaker gravity than we experience at the surface, tick faster than our clocks by about 45 microseconds per day due to general relativity. At the same time, their orbital speed causes a slight opposing effect. Special relativity predicts that moving clocks tick slower, costing them about 7 microseconds per day. The net result, even after accounting for their speed, is that satellite clocks gain about 38 microseconds per day over clocks on the ground. If you did not correct for this, GPS positioning would drift by roughly 10 kilometers per day. We correct for it because Einstein's equations tell us to, and because they are right. Near a black hole, this effect is extreme. Time near the event horizon passes so slowly, relative to time far away, that from the outside observer's perspective, your clock essentially stops as you approach the horizon. They never see you cross, but from your perspective, your clock is running perfectly normally. You fall through. You have not experienced any slowdown. The universe has not conspired to pause you at the horizon from your own point of view. What is happening is that there is no single, universal now. There is no cosmic clock that ticks the same for everyone everywhere. Two observers in different gravitational fields can have equally valid but completely different experiences of the sequence and timing of events, and both are correct within their own frames of reference. The frozen observer and the falling astronaut are not disagreeing about facts. They are experiencing genuinely different physical realities, both of which are equally real, equally valid, and equally described by the same equations. General relativity does not give you one story of what happened. It gives you the correct story for each observer, and the two stories do not have to match. Now we get to the part where even the physicists start arguing. Here is the problem. When you fall into a black hole, you carry information, not just data in the casual sense, but physical information. The exact state of every particle in your body, the precise quantum configuration of every atom, the complete description of everything you are made of. In physics, this information is considered indestructible. One of the deepest principles of quantum mechanics is that information is never truly lost. It may be scrambled beyond any practical recovery, but it must, in principle, still exist somewhere. Black holes appear to violate this. Stephen Hawking showed in 1974 that black holes are not perfectly black. They emit a faint glow of radiation, now called Hawking radiation, caused by quantum effects at the event horizon. Over an extraordinarily long time, a black hole radiates away its mass and eventually evaporates entirely. The problem is that Hawking radiation, as originally calculated, is perfectly thermal. It is random. It carries no information about what fell into the black hole, which means that when the black hole finishes evaporating, all the information that ever fell in, including you, appears to be gone, permanently, in violation of quantum mechanics. This is the black hole information paradox. And it is not a small problem. It is a collision between two of the most successful and well-tested theories in the history of physics, general relativity and quantum mechanics, and they are telling contradictory stories about what happens to information in a black hole. Physicists have been arguing about this since Hawking first raised it. There are several competing proposals. Some argue the information is encoded subtly in the Hawking radiation, scrambled but theoretically recoverable. Some argue it escapes through exotic mechanisms. Some argue that black holes do not fully evaporate and instead leave behind a stable remnant containing the information. Some, and this is the most unsettling option, have argued that the principle of information conservation might simply be wrong. We do not know the answer. This is not a mystery where the solution is known to experts and just hasn't been explained to the public yet. This is a genuinely open problem at the frontier of theoretical physics. Some of the most brilliant minds working on fundamental physics have devoted careers to it. As of today, it is not resolved. What we know is this: whatever the resolution is, it will require us to change something deep about how we understand either gravity, quantum mechanics, or the nature of information itself. There is no comfortable solution that leaves everything intact. In 2012, a group of physicists, Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully, collectively known as AMPS, published a paper that made things considerably more uncomfortable. They argued that if information is preserved in Hawking radiation, then something dramatic must happen at the event horizon. Specifically, they proposed that a freely falling observer would not pass through the event horizon unharmed. Instead, they would encounter a wall of high-energy radiation, a firewall, that would instantly destroy anything trying to cross. This directly contradicts what general relativity says, which is that the event horizon is locally indistinguishable from empty space, and that a freely falling observer notices nothing special at the moment of crossing. The firewall paradox forced a choice. Either the principle of information conservation is violated, or the principle that freely falling observers experience nothing special at the event horizon is violated. Both are deeply held beliefs in physics. Both cannot be simultaneously true if the AMPS argument holds. The debate that followed was intense. Physicists, including Stephen Hawking, proposed that the event horizon might not be a sharp boundary at all, but something fuzzier and more complex. String theorists proposed that black holes might be vast quantum objects called fuzzballs, with no interior and no singularity, just a dense tangle of strings at the Planck scale. Others proposed that the paradox reveals a deep connection between quantum entanglement and the geometry of spacetime itself. In 2013, physicists Juan Maldacena and Leonard Susskind proposed what has become known as the ER equals EPR conjecture, the idea that entangled particles are connected by wormholes, and that the smooth interior of a black hole might actually be constructed out of quantum entanglement between the black hole and its Hawking radiation. Under this view, severing that entanglement, which preserving information would require, would necessarily destroy the smooth spacetime on the other side of the horizon, eliminating the need for a firewall while preserving information. ER stands for Einstein-Rosen bridge, the technical name for a wormhole. EPR stands for Einstein-Podolsky-Rosen, the technical name for quantum entanglement. The equation ER equals EPR is either one of the deepest insights in the history of physics or a conjecture still waiting for its proof. Either way, it has fundamentally reshaped how physicists think about the relationship between spacetime and quantum information. None of these proposals have been definitively established. The firewall debate is ongoing. The information paradox remains open. The interior of a black hole remains, in the most literal possible sense, unknown territory. What the debate has produced, however, is a growing conviction among physicists that black holes are not just exotic astrophysical objects. They are windows into the deepest unresolved tensions in our understanding of reality itself. Let's take a breath and be honest about the line between what we know and what we are still working out. We know black holes exist. We have directly imaged two of them, M87 star in 2019 and Sagittarius A star in 2022, using the Event Horizon Telescope, a global network of radio observatories acting as a single Earth-sized dish. The images matched the predictions of general relativity with extraordinary precision. We know gravitational waves exist and have detected dozens of events caused by merging black holes using the LIGO and Virgo detectors. The signals match general relativity's predictions. The masses, the merger dynamics, the ring down of the final merged black hole, all consistent with theory. We know time dilation is real and measurable. We know event horizons behave as general relativity predicts, at least from the outside. We know Hawking radiation is predicted by extremely well-tested physics, even though we have not yet directly detected it from an astrophysical black hole. The signal from any black hole we could realistically observe would be far too faint to measure with current technology. However, physicist Jeff Steinhauer at the Technion in Israel has created analog black holes in the laboratory, using cold rubidium atoms in a state called a Bose-Einstein condensate. where a sonic horizon mimics the event horizon in miniature. These acoustic black holes have been observed to emit an approximately thermal distribution of analog Hawking radiation, with entangled particle pairs behaving exactly as the theory predicts. The physics is of sound rather than gravity, but the underlying quantum mechanics is the same, and the results have substantially increased confidence in Hawking's original mathematics. What we do not know is what happens at the singularity. Our equations tell us nothing reliable there. We do not know what happens to information. We do not know the ultimate fate of a fully evaporated black hole. We do not know whether the interior is genuinely what general relativity describes, or whether quantum effects modify it fundamentally. We have extraordinarily good maps of the territory right up to the edge. Beyond that edge, the map is blank, and the blank part of the map is where the most interesting physics in the universe is waiting to be found. So, what actually happens when you fall into a black hole? From the outside, you freeze at the horizon, redden, fade, and vanish. Time, from the perspective of someone watching, stops for you at the edge of everything. From the inside, you fall through, uneventfully, into a region of the universe that no information ever leaves. Depending on the size of the black hole, you may have microseconds or hours or days before the singularity, that gap in our understanding of physics, becomes your final destination. Both of these things are true. Both are real. They are not contradictions. They are two perspectives on a universe in which time is not absolute, in which the geometry of space itself can be curved and warped and stretched, in which our deepest theories produce answers that are simultaneously precise and incomplete. The honest answer to the question, what actually happens when you fall into a black hole, is this. We know more than you might expect, and less than we would like. We know the geometry. We know the experience broadly of the fall. We know what the event horizon means and how time behaves near it. We know what our equations say, and we know where our equations stop being trustworthy. What we do not know is what lies at the bottom, whether information is preserved or destroyed, whether the interior is what we think it is or something else entirely, whether the singularity is a real physical object or a placeholder for a deeper truth we haven't found yet. Black holes are the most extreme environments the universe produces. They are places where gravity wins over everything, over matter, over light, over the information that defines what it means for something to have happened. And they are places where the two greatest theories in physics, general relativity and quantum mechanics, look each other in the eye and give different answers. Whatever resolves that disagreement will change what we know about reality at the deepest level. We are still waiting to find out what it is.